Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing electric potential and this is lecture number 5. In previous lectures, we have discussed about qualitative and quantitative idea about electric potential, and also we have discussed about electric potential difference, and in chapter number 1 we have discussed briefly on electric field. Electric field due to a point charge, electric field due to system of charges. Similarly, in this chapter means on electric potential, we have discussed the electric potential due to a point charge and electric potential due to system of charges. In this lecture, we will discuss relation between electric field and potential. Relation between electric field and potential. Okay, let's consider a point charge. Let this point charge is Q. Let's take positive charge, and as we know, electric field produced by the point charge in all directions are symmetric. Okay, electric field is symmetric all around the point charge, and as we know, range of electric field is up to infinity. Okay, let's consider all these are electric field lines. Okay, let's consider any point in the electric field. Okay, let's consider any point in the electric field. Okay, let's consider this point P. At a distance r from the point charge, you may take any point P. Okay, in the electric field. Let's consider this is the point P in the electric field. Electric field at this point is k q by r square, and as we know, electric field is a vector quantity. Okay, again, potential at this point means potential due to point charge is k q by r. Okay, since V inversely proportional to r, this is positive charge plus q, electric field is outward in all directions, so electric potential is inversely proportional to distance from the point charge. From this equation, it may be concluded that potential decreases along the direction of electric field and vice versa. Very important. Potential decreases along the direction of electric field. See, as distance from this point charge goes on increasing along the direction of electric field, potential will go on decreasing. So potential decreases along the direction of electric field and vice versa. Means if we move opposite to the direction of electric field, then potential will increase. So if you move along the direction of electric field, means away from this point charge, from positive point charge, then potential will decrease. Okay, simply remember, very easy to remember, potential decreases along the direction of electric field means as the distance along the electric field increases, potential decreases. Okay, this is simple point, just remember it. Okay, then our aim is to find relation between electric field and potential. Very simple. Okay, let's consider a point charge Q. Let's consider electric field along this direction. You may consider any direction. Okay. This is any point A. As we know, potential is k q by distance. This is any point A. Okay. Let's place here an unit charge means test charge. Okay. As we know, potential difference is defined as potential difference between any two points in the electric field, I am writing completely, in the electric field is defined as the amount of work done to move an unit charge by external agent. Potential difference, we have discussed it. Potential difference between any two points in the electric field is defined as the amount of work done. The amount of work done to move an unit charge, means a test charge or unit positive charge, move an unit charge by external agent. Okay, let's discuss it. If you place an unit charge or plus Q at point A, then it will experience a force along the direction of electric field. We have taken this is positive charge, field created by positive charge. So electric field is away from the positive charge. This is also positive charge. This positive charge will be repelled by the field creating charge. So force experienced by this unit charge or positive charge due to electric field is equal to QE. As we know, electric field is force per unit charge. So force experienced by this charge Q is QE, means force experienced by this unit charge or charge Q is along the direction of electric field. But we have taken the definition of potential difference between any two points in the electric field is defined as the amount of work done to move the unit charge by external agent. Okay, let the charge is moved from A to B. These are the 2 points. Let distance between AB is delta R. Distance between delta A and B is delta R. See, if we just place a charge here plus Q, this charge is placed at position A and is released. This charge is placed at A and is released. So obviously it will experience a force along the direction of electric field and move away from point A to point B and again along the direction of electric field. And here the charge will move with acceleration. But here the important point is work done by external agent, and next important point is the motion of charge. Very important, the motion of charge, motion of unit charge should be with uniform speed or with same thing, uniform speed or with constant kinetic energy. We have discussed it. Okay, what is the concept behind it? This charge should be moved from one point to another point, say from A to B, by external agent. First, let's consider this point first. The charge should be moved from A to B by external agent. Okay, work done by external agents. But this is the force experienced by the charge due to electric field. Okay, again, if electric field is along the direction of electric field, then we may apply an external force opposite to the direction of force experienced by the charge. This is external force. Second point, the motion of unit charge should be with uniform speed or with constant kinetic energy. What is this concept? Why it is written so? If speed is constant, obviously kinetic energy is constant. Let's recall about the basic concept of work. Work is either change in potential energy or change in kinetic energy or change in both. This is the basic concept. Just keep it in our mind. Work is either change in potential energy or change in kinetic energy or change in both. Work is either change in potential energy or change in kinetic energy or change in both. Okay. So we have to move the charge from one point to another point, from point A to point B through a displacement delta R by the help of external force. Why kinetic energy is kept constant? This is a question. Work is either change in potential energy or change in kinetic energy or change in both. Means if the charge is left here, it will move with electric force, means it will move with acceleration, but work should be done by external force. To move the charge uniformly, magnitude of external force must be equals to magnitude of force experienced by the charge due to electric field. So these two forces are opposite in direction, thus resultant force will be 0. If charge is moved with acceleration, means if resultant force acts on the charge will move with acceleration. An accelerated particle gains kinetic energy. Okay, means if speed changes, then kinetic energy changes. Work is either change in potential energy or change in kinetic energy or change in both. Here our concept is we have to find relation between electric field and potential. Potential is due to potential energy. Potential is due to potential energy. Okay, it means whole amount of work. This is the question. If someone asks why the charge should move with constant kinetic energy, to find potential difference, because whole amount of work should be in the form of potential energy. Whole amount of work should be in the form of potential energy, so that we can calculate potential difference. Because the basic concept we know, potential difference is amount of work done by external agent to move a charge from one point to another point per unit charge. We have discussed it. Potential difference is work done by external agent per unit charge. We have discussed it. Potential difference is equal to amount of work done by external agent per unit charge. Here total amount of work by external agent should be in the form of potential energy. Work is equals to potential energy only without change in kinetic energy. Work is only change in potential energy. Means total amount of work will be in the form of potential only and only. So we have to keep kinetic energy constant. This is the basic principle. Okay. I am erasing it. Then let's first find work done to move the charge from point A to B by the help of external agent. See, direction of external force is opposite to the direction of electric field. To move the charge with uniform speed, resultant force should be 0. If resultant force is 0, then acceleration is 0. If acceleration is 0, then velocity is constant. If velocity is constant, then both magnitude and direction is constant. If direction is constant, if direction of velocity is constant, then magnitude here also constant, because resultant force is 0. So magnitude constant means speed is constant. So charge should move with uniform speed. So work is due to external agent, external force dot displacement is delta. Here we will take external force negative, as it is opposite to the direction of force due to electric field. This is force experienced by the charge due to electric field. We are applying external force so as to move the charge with uniform speed. Magnitude should be equal and direction should be opposite. So work is equal to external force, that displacement. This external force means this external force is equal in magnitude but opposite in direction to the force experienced by the charged particle due to electric field. So we are taking negative. Okay. Then as we know, this is potential difference is work done by external agent to move the charge from A to B per unit charge. This is our previous concept. So here, potential difference between A and B. Okay. Is delta V, work done by external agent dot delta R divided by Q. See, magnitude of electric force is QE. Since magnitude of external force is equal to magnitude of electric force, so delta V is equal to external force minus QE. Force due to electric field is QE. Force due to external force is minus QE. We are applying this force. So minus QE dot delta R divided by Q. Q get cancelled. So finally we may write potential difference between A and B is minus E dot dr. Sorry, delta R. Minus E dot delta R. This is our formula. Potential difference is minus E dot delta R. Okay. I am writing here the formula. Formula for potential difference between any 2 points in an electric field. The 2 points are separated by a distance delta R. Okay. Then delta V is equal to minus E dot delta R. Okay. Minus E dot delta R. Why minus? Because external force is opposite to the direction of force experienced by the charge due to electric field. Okay. If you need only value of potential, then you may take only E dot delta. We will decide whether it will be finally positive or negative. Using this point, potential decreases with increase in distance. Okay. Magnitude of potential is E dot dr. No need to take positive. This will be applied in numericals. We will apply it in numericals. So, using this concept, potential decreases along the direction of electric field. If we are moving along the direction of electric field, or we are moving opposite to the direction of electric field. Along the direction of electric field, potential will decrease. Opposite to the direction of electric field, potential will increase. Okay, this is the concept. Then this is fundamental formula. Okay. As you see, units of potential. Units of potential is, or potential difference is volt. Electric field, or we have taken it previously, volt. Okay. Units of potential is volt. Electric field is Newton per coulomb into meter, Newton meter per coulomb. Oh, sorry. Units of potential, I am writing completely. Units of electric field, sorry. Electric field. Units of electric field, sorry. Not potential. Units of electric field, we have taken Newton per coulomb. And here, see, potential is in volt. This is electric field. Distance or delta R is in meter. So units of electric field is volt per meter. See, this is volt, this is meter. Units of electric field is volt per meter. Sometimes in board level questions it may be asked to prove that volt per meter is equal to Newton per Coulomb. Prove that volt per meter is equal to Newton per Coulomb. Okay. Volt means potential is equal to work done per unit charge. We know it. Then volt is equal to, this is potential, volt is equal to 1 volt. This implies 1 volt is equal to 1 joule per Coulomb. I am taking volt per meter. 1 volt per meter. In place of volt I can write joule per Coulomb divided by meter. Again it is joule per Coulomb meter, and 1 joule is 1 Newton into meter. Newton into meter is joule divided by Coulomb meter. Meter get cancelled. Thus 1 volt per meter is equal to 1 Newton per Coulomb. See, too simple. We have proved 1 volt per meter is equal to Newton per Coulomb. 1 volt. Potential difference is equal to work done per charge. Potential difference is volt. Work is joule. Charge is Coulomb. So 1 volt is equal to 1 joule by Coulomb. So 1 volt per Coulomb. 1 volt per meter. Volt per meter is units of electric field. Volt per meter. In place of volt I can write joule per Coulomb divided by meter. This comes joule divided by Coulomb meter. 1 joule is equal to 1 Newton into meter divided by Coulomb meter. Meter get cancelled. Thus 1 volt per meter is equal to Newton per Coulomb. Too easier. Okay. This is the concept. So this is valid. This formula is valid. This formula is valid in uniform electric field. Very important, this formula is valid in uniform electric field. Suppose we are considering non-uniform electric field. Okay. Suppose this is a non-uniform electric field. As we have discussed, where electric field lines are crowded, their electric field is stronger. So electric field is stronger in this region and becomes weaker and weaker as we move along the direction of electric field. Electric field also decreases along its direction. Let's consider any point. Okay, this point is A, and here we have placed an unit charge. Okay, here we have placed a unit charge. Let it be displaced through a very small displacement to a point B. AB is dr. Dr is very, very small. So since this is the direction of electric field, this is the force experienced by electric field. Electric field is QE, but potential difference is equal to work done by external force to move the charge from A to B, per unit charge. So we have to apply an external force. External force is also equals to QE. External force is also equals to QE, but opposite in direction means minus QE. So this external force is applied on this unit charge. So the unit charge is moved from A to B through a very small displacement, AB, that's equals to delta R. Okay. Then work done is let dW is equal to minus QE dot dr. Then total work is integration minus QE dot dr. Okay. Then, as we know, see, this electric field is non-uniform. If you take this point is C, this point is D, or if you take from B to C, this is also dr. From C to D, this is also dr. Okay. So here also at point B, the charge will experience force due to electric field and external force, the same thing. So the whole distance along the direction of electric field in a non-uniform electric field may be divided into a number of small segments, each of displacement dr. So total work is integrated QE that dr. Okay. Then total potential difference dV is equal to total work per unit charge, total work per unit charge. So I have written here, then total potential difference is integration of minus QE dot dr divided by Q gets cancelled. So here potential difference is minus integration of E dot dr. Suppose point A, position vector for point A is R1, position vector, let final point is at any point X is R2. Okay. From R1 to R2, taking limits or potential varies from position R1 to position R2. This is valid. This is valid in non-uniform electric field. These concepts are described beautifully in some good books. Okay, what is for uniform electric field and what is for non-uniform electric field. This is for non-uniform electric field. This is for uniform electric field. This is for uniform electric field. This is for non-uniform electric field. This is described in very beautiful manner in different books. Okay. Next point. These are the formula. You should remember it. Then we will move to some numericals, very easy numericals, but the concept we'll use this, very easier to apply this formula in numericals. So magnitude of electric potential difference is equal to E dot dr. No need to take negative. We will apply this principle, potential decreases along the direction of electric field and vice versa. Means potential increases opposite to the direction of electric field. Okay. I am erasing it. Okay. Question number 1, on uniform electric field, uniform electric field of let 100 volts per meter, 100 volts per meter exist in vertically downward. Very easy question, just we will apply the formula, one line problem. Means solution is in one line, but we have to write like this, vertically downward direction, vertically downward direction. Find increase in potential, find increase in potential as one moves upward through a distance of 100 centimeters. Electric field is existing in vertically downward direction. This is vertically downward direction, and magnitude of electric field is 100 volt per meter. So as one moves from one point to another point through a distance of 100 centimeter, means 1 meter, what will be? Increase in potential energy, increase in potential. Okay, increase in potential. See, this is the direction of electric field. Electric field is in downward direction. If you move upward, means if you move opposite to the direction of electric field, then potential will increase. Potential decreases along the direction of electric field. Potential increases opposite to the direction of electric field. This is opposite to the direction of electric field. As one moves upward, vertically upward, then here increase in potential means potential difference between these 2 points. Okay, E dot dr, delta only magnitude. So potential difference is, electric field is 100 volt per meter and distance is 1 meter. Meter get cancelled, so potential difference is 100 volt. But as we move opposite to the direction of electric field, then potential difference is positive, because potential increases as we move opposite to the direction of electric field, so it is positive. Okay, very easy. Just you should know what is the concept of electric potential difference. So we have applied to a very easier question than question number 2. Just a minute. Okay, it's all right. Question number 2. 100 joule of work, 100 joule of work is done against an electric field E. Electric field E, to move a charge of 0.01 coulomb from A to B, means any 2 points A and B, from A to B, find potential difference. Find potential difference if magnitude of electric field is, let again, 100 volt per meter. Okay, we have to find potential difference, but work is done against the electric field. If we move along the direction of electric field, potential decreases. If we move opposite or against the electric field, then potential will increase. Okay, then potential difference, again the same form, E dot dr. Okay, so E dot dr, so E dot delta, no need to take positive negative. We know that if potential decreases along the direction of field, potential increases opposite to the direction of electric field. The charge is moved against the electric field, means if we move against the electric field, against means opposite to the direction of electric field, then potential will increase. Then E, 100 volt per meter. No, this is, I think I have to change the question. Yes, no, it is given. Work is given, work done is given. Work is equal to 100 joule and charge is equal to 0.01 coulomb, and we have to find potential difference. No need to take E. This is question. I am framing the question here itself. So this is the question. Then work is given, charge is given, then potential difference is work divided by charge, 100 divided by 0.01 and it will come 10 to the power 4 volt. So it will be in positive because the charge is moved against the electric field. Along the direction of electric field, potential decreases. So it will be 10 to the power 4. Okay. Or we may change A to B. Find potential difference if I mention VB minus VA. VB minus VA. So VB is more, VA is less. Okay. Against the direction of electric field, this is the direction of electric field from A to B, from A to B. So if here potential is VA, here potential is VB, then VB is greater than VA. So final answer is in positive. No need to take electric field because the question is framed here itself. Okay. Then question number 3. These are easier questions. Question number 3. Let in an uniform electric field. This is an uniform electric field. As we know, if electric field lines are parallel and equidistant, if the electric field lines are parallel and equidistant, then electric field is uniform. So this is uniform electric field. It is given that magnitude of electric field, let 100 volts per meter or Newton per coulomb, whatever you may take. Inside this, in this uniform electric field, let's consider an equilateral triangle A, B, C. Okay. Let each side is 1 meter. Let each side is 1 meter. It is asked, find potential difference. Find potential difference between, or find potential difference first with VA. Magnitude, let magnitude of electric field is given 10 Newton per coulomb or volt per meter, whatever it is given. Sorry, 100. We have taken 100. Okay. It is given. I have written it. Find potential difference between A and B. VA minus VB. Number 2. Find potential difference between B and C, means VB and VC. These are 2 questions. This is uniform electric field. Then first we have to find potential difference between A and B. Between A and B. A and B. Okay. See, this is the direction of electric field. So as the distance increases, point A comes. Okay. So obviously for first bit, VB is greater than VA. VB is greater than VA as electric field, means direction of, along the direction of electric field, potential decreases. So VB is more than VA. We have to find VA minus VB. Okay. Then VA minus VB means delta V is equal to E dot dr. Okay. Electric field is 100 volt per meter. Then distance between A and B, this is the resulting distance. Since this is equilateral triangle, this is 60 degrees. This is point A, this is point B. Along the direction of electric field, this is the distance. Okay. Then this distance is delta R, not here, delta R. This distance is delta R. Let this point is D. Then BD or delta R is equal to 1 cos 60, and this is equals to cos 60, means 1 by 2, 1 into 1 by 2 meter. Okay. Then E, electric field is 100 volt per meter, and this is 1 by 2 meter. Okay. VA, VB, this point, potential at this point is VB, VA, distance between them is delta R, and delta R is equal to 1 cos 60, 1 cos 60 means this is half meter, okay. This is half meter, then 100 into half meter is equal to 50 volt, okay. Is it correct? Yes, VA minus VB, VA minus VB, sorry, it will be negative. Potential decreases with increase in distance, potential increases with increase in distance, okay. Take it first, then I will move to second bit. Final, complete, okay. Second bit, will I erase it? Second bit. Okay. Second bit, VB minus VC, VB minus VC here, VB minus VC. Again, our formula is, this is also delta V, this is also delta V, E dot delta R, E dot delta R, okay. So, why we are taking always a dot product? Because this point we are finding between any 2 points C. Suppose this is an electric field, this point is A, this point is B, this displacement is delta R, okay. So, here angle between the electric field and delta R is 0 degree. If point B is taken here, then angle will be theta. If point B is taken here in the electric field, then angle will be, this is theta 1, this is theta 2. So point B may be taken in any direction, so that we are taking dot product, okay. Then VB minus VC, VB minus VC. Electric field decreases with increase in distance, so VB is more than VC. Electric field decreases with increase in distance, so VB is greater than VC, so delta V is E. Electric field is 100. Distance is 1 meter, 100 into 1, that is equals to 100 volt, but VB is greater than VC, so it is positive. VB is greater than VC, so it is positive. Okay. Next question. In an uniform electric field, we are taking in uniform electric field. Next question, let's take it. Question number 4 or 3, I have not remembered. Let's take 4. Increasing. This is an uniform electric field. Let's represent an uniform electric field. Electric field lines are parallel and equidistant. Electric field is E. Okay. We'll take any value of E. This is a square. This is a square in the electric field A, B, C, D. Let any side is, each side is 1 meter. Okay. Each side is 1 meter. Let the electric field is 20 volt. Electric field is 20 volt per meter, and it's a uniform electric field. First bit. It is asked to find VA minus VB. Let's find it, then we'll move to second step. We'll find potential difference between A and B, VA minus VBC. Potential decreases along the direction of electric field. Potential decreases along the direction of electric field. This is the direction of electric field, so VA is greater than VB. So, potential difference between VA and VB. Let's take delta V. Delta V is equal to E dot dr. along this direction of electric field and AB is 1 meter, then VA minus VB electric field is 20 into 1, that's equals to 20 volt. It is positive because VA is greater than VB, so finally we will take positive. Okay, is it clear to you? Then next bit. Find potential difference between VA minus VD, VA minus VD. See, this is 1 meter, this angle is 90 degrees. Then potential difference VA minus VD is, let's take delta V. Electric field E dot delta, electric field is 20, delta R is, this is 1 meter, and this component means AD. Delta is 1 cos 90, that's equals to 0. Okay, 1 cos 90 is 0, so potential difference between A and D is 0. Okay, final, this is AB 1 meter, this is AD also 1 meter, but we have taken that product. Okay, we have taken that product so that we didn't multiply directly 1. Delta R means this is direction of electric field, this is the delta R. Okay, electric field delta R, angle between them is, this is electric field A to B, angle is 90 degree, or directly take 1 cos 90. Okay, E dot delta R means this is E delta R cos theta, E delta R cos theta. Okay, 0. Okay, then another bit on this diagram, number 3. Find VB minus VD, VB minus VD. Okay, here potential at D is greater than potential at B. Potential decreases along the direction of electric field. Potential decreases along the direction of electric field. So this is D, this is B, electric field increases, potential decreases. So VA minus VD, let's take delta V, E dot delta. Okay, see, if this is 1 meter, each side is 1 meter, then this is root 2 meter. This is root 2 meter. Okay, so between B and D, direction of B and D. Okay, you have to take direction. This is root 2 meter. This is resulting distance between B and D. So electric field is 20. Resulting distance is root 2. This angle is 45 cos 45, as we have taken previously. Sorry, this is B. This is B. Okay, angle between BD and DC means this is direction of electric field. Angle between displacement, delta R, or this is delta R, and electric field is 45 degree. Okay, then it is equals to 20 into root 2 into cos 45 is root 2, that's equals to 20 volt. So VB minus VD, sorry, I have written here, okay, right. VD is greater than VB. We are finding VB minus VD, but VD is greater, or you may write VB is less than VD. VB is less than VD, so we will take it minus. Potential decreases along the direction of electric field. Potential decreases along the direction of electric field. Okay. Now another concept, if electric field, we do consider electric field with respect to origin. Electric field with respect to origin means in Cartesian frame. Okay, let's consider this is origin of a coordinate system, x, y, z. This is origin 0, 0, 0. This is any point P, and this is direction of electric field. Okay, and position vector for electric field is E. Position vector for electric vector is E with respect to origin. Okay, electric field. See, this is x-axis, component of electric field along x-axis Ex, along y-axis Ey, along z-axis Ez. Okay. The previous concept from mechanics in kinematics, you have already studied about frame of reference, Cartesian coordinate system, frame of reference, etc. Then, resulting electric field in the coordinate system may be given as Ex plus Ey plus Ez, or we may write Ex I cap is unit vector along x-axis, Ey j cap is unit vector along y-axis, and similarly Ez k cap is unit vector along z-axis. You know it. Okay. Where is it? Then, as we know, potential difference, small potential difference, dV is equal to E dot dr. Okay, small potential difference dV is equal to E dot dr. Okay, R vector. See, if coordinate of point P are x, y, z, its coordinates, x coordinate is x, y coordinate is y, and z coordinate is z, then position vector is given as xi cap plus yj cap plus z k cap. Now use this formula. dV is equal to E dot dr. dV is equal to E dot dr. Small displacement dr and small potential difference dV. In place of E, you will write exi cap. Sorry, another bit. If R is this much, then dr. This is dr. Then dr. R and dr. Then it may be dxi cap plus dy j cap plus dz k cap. Very simple, very simple. dr, R is equal to xi cap plus yj cap plus zk cap. So dr is equal to dxi cap plus dyj cap plus dz k cap. Only d. Differentiating both sides. Okay. dr is equal to dxi cap. Okay. This is minus. Okay. dV is equal to minus E dot dr. So here dV is equal to minus E. In place of E, we will write exi cap plus ayj cap plus ez k cap dot dr. In place of dr, we will write dxi cap plus dyj cap plus dz k cap. You know that product I cap dot I cap 1, I cap dot j cap 0, I cap dot k cap 0. Component method of that product is know it. Then dV, change in potential difference, is minus exi cap dot dxi cap. Ex dx. Okay. And exi cap dot dyj cap is 0, since I cap dot j cap is 0. Exi cap dot dz k cap is 0, since I cap dot k cap is 0. And in similar form, we may write Ex, Ey, dy plus Ez, dz. Okay. In vector form, you may also use I cap j cap k cap. Okay. Sorry, this will not vector. Sorry. I cap that I cap 1, dot product is scalar quantity. Okay. Or I am doing knowingly. Okay. I am doing knowingly. Of course, you know dot product A I cap dot B I cap is AB. Okay. Ay j cap, by j cap, then ay by. Okay, that product is scalar. So this is dV. Okay. Now I will erase it. No need to keep the diagram. Suppose I want potential difference dV along x-axis, then obviously it will be dVx. Okay. Then electric field only along x-axis. Okay. Electric field along x-axis. Electric field along x-axis. I may take it Ex. I may take it Ex magnitude of electric field. Then it will be C. Electric field is, potential difference along x-axis is electric field along x-axis dot dr. So potential difference dVx is equal to Ex. In place of dr, I can write dx, Ex dx. Okay. Then Ex is, means in differential form, this is partial differentiation. We need electric field only and only along x-axis. So electric field along x-axis, partial differentiation of potential along x-axis, and this is the concept. So electric field is, again this is minus, this is minus, this is minus, so this is minus. Okay. Minus dVx by dx. So the basic concept again we may apply. Potential decreases along the direction of electric field. Potential increases opposite to the direction of electric field. Okay. In similar form, this is potential along x-axis. Similarly, electric field in vector form, you may write I cap, only magnitude, partial derivative. So electric field, similarly electric field along x-axis Ex, along y-axis A1, partial derivative with respect to y, or Ey in vector form into j cap. Similarly, Ez, partial derivative, and Ez in vector form into k cap. And now, this is a formula for electric potential difference using Cartesian coordinate system and electric field. Just put here, this is in place of Ex. Well, I erase it to complete the equation, means complete form of electric field in vector form is minus this is in vector form. Okay. So magnitude of electric field is square root of C. Ex, Ey and Ez are rectangular components of electric field in Cartesian coordinate system. Then magnitude of electric field is square root of Ex square plus Ey square plus Ez square. All these you know in vector, position vector. Okay. If position vector of a point is A, the coordinates are Ax, Ay, Az, then A vector magnitude is square root of Ax square plus Ay square plus Az square. Okay. This is about the electric field. And see, now suppose I am writing here electric field along z-axis is delta V by delta Z. Okay. Then electric field is negative of potential gradient. Potential gradient along z-axis, potential gradient is partial derivative of potential with respect to z. Okay, so electric field is a negative of potential gradient. Okay. Some numerical, some one or two numerical, very easy numerical. Okay. Then we'll end our class. Question number 1. electric field, sorry, electric potential. Electric potential at any point, electric potential at any point is given as V is equal to 4x square volt. Okay, find electric field. Find electric field at a point P. Coordinates are given. Suppose 1 meter, 0, 0. Okay. Then here electric field. See, this is along only x-axis. We no need to culture a lot. Potential is 4x square, and as we know, it is given in terms of x coordinate. B is equal to 4x square. So we may write here Vx is equal to 4x square, and electric field along x-axis is only magnitude, and this is equals to 8x, and value of x is 1 meter. Okay, then electric field along x-axis is 8 into 1. So value of electric field is 8 volt per meter. Okay, 8 volt per meter. Magnitude is 8 volt per meter. Okay. Find the electric field at a point, means magnitude of electric field. No need to take negative. Magnitude is only 8 volt. No need to take negative or solve. Okay. Next question. Potential. Next question. Potential at a point P is given as V is equal to 6x minus 8xy square minus 8y plus 6yz minus 4z square. Potential at any point P is given as V is equal to 6x minus 8xy square minus 8y plus 6yz minus 4z square. Suppose this is given in volt. This is given in volt. Find, or what is electric field? What is the electric field at coordinates are given at origin? Suppose I am taking origin. If coordinates are given, coordinates of origin are 0, 0, 0. You use any coordinate for origin. Okay, you know the position vector. If the coordinates of point P are x, y, z, then position vector is x minus 0 I cap, y minus 0 j cap, and z minus 0 k cap takes sum. X minus 0 I cap plus y minus 0 j cap plus z minus 0 k cap, since coordinates of origin are 0, 0, 0. If any other values were given, then x minus given value of x at origin. Okay. So we have to find electric field at potential. So electric field is partial derivative. Electric field along x-axis minus dv by dx. Just differentiate it. dv in place of v. We are doing partial derivative, means if you take dv by dx, then partial derivative of x with respect to x-axis. Okay. Delta v by delta x, del v by del x. Del v by del x is we are going to find. So del v by del y is 0 and del v by del z is 0, because while taking partial derivative we have to only consider about x coordinate. Y and z coordinates are taken to be constant, since y and z coordinate are taken to be constant. So this is 0, this is 0, means dvy or any value of y value, any value of y, any value. Okay, 0. Suppose it is y square, y cube, it is z square, any value of y or z is 0 because we are considering electric field along x-axis. Okay, then taking partial derivative, 6x is 6, partial derivative of x is x. This is minus x y square, so it will come minus 8y square. Minus 8y is 0. Here 8x y square. So partial derivative of x is x. Okay. Then minus 8y square, y is constant, 8 is constant, so 0. Minus 6yz is 0. Minus 4z square is 0. So magnitude of electric field is minus 6 minus 8y square. Del of y is 0, so 0. Six x, 8xy square. Okay, this is 6. This is minus y. This is minus y square. This is minus y square. This is 0. This is 0. This is 0. Okay, this is 8 volt per meter. Similarly, electric field along y-axis, along y-axis, along y-axis. So 6x differentiation is 0. Along y-axis, minus 8x into 2y. Minus 8x, partial derivative of y square is 2y. Okay. Minus 8y means 8 plus 6y there, minus 6z, minus 4z square, z is constant, 0. So electric field along y-axis, minus 8x into 2y, minus 8, minus 6, okay. Minus 16, 8 into 2, 16, x is 8 into 0, into 2 into 0, minus 8, minus 6, z is 0, 0, so it is minus 8 volt per meter. Similarly, magnitude of electric field, Ez along z-axis, this is 0, minus xy are constant 0, minus 8y 0 along z-axis, so plus 6y, minus 4z square means 8z, so electric field along z-axis magnitude 6 into y is 0, minus 8 into z is 0, that's equals to 0. Okay. Then magnitude of resulting electric field is square root of Ex square. Six x 1 or 8 y square, y is 0, so this is 8, not 6, this is 8. Sorry, this is 6. 8 into 0, this is 6, minus 6. Some mistakes are there. Y is 0, 6x, so 6, partial derivative of x is 1, so this is 6. 6 minus 8, y square, this is 0, this is 0, this is 0. Okay. Y is 0, so 8 into 0 is 0, this is only 6, or this is minus 6. Okay. Ey, 6x 0, 8x into 2y, 8x into 2y, minus 8, okay, Ey. So inside bracket. This is inside bracket. This is negative. Okay. This is minus, so this is 6 minus 6, so this is negative. 8x, x is 0. 2y, y is 0. Minus 8. So this is minus, this is inside the bracket, this is inside the bracket. This is 8. This is, sorry, this is total 0. This is minus 8 volt per meter. Okay. Then this is Ez. 6x 0, 8xy square 0, 8y 0, 6y, 8z, y is 0, z is 0, thus it is 0. So, magnitude of electric field means Ex square plus Ey square plus Ez square. So, that's equals to minus 6 square, and Ey is minus 8 square. So this will come 64, 36, 100. So 10 volt per meter. Okay, take it. $10 volt per meter. This is our answer. Checking the calculation whether it will come in wrong in some hurry mode. Okay. This is right. Then another type of numerical. Will I erase it? Will I erase it? Just I was checking it. I have taken some more time to check it. I thought whether there may be some wrong due to my hurriness. Okay. Next question. Let electric field, I am just writing the expression whatever I am thinking. Electric field is given as 2xi cap minus yj cap plus z k cap. Find potential difference between point P. Suppose coordinates are given to 0, 1 and Q. Suppose potential is given 0, 0, 0 or 0, 1, 0, any value. 0, 1, 0, all are in meter. This is meter, this is meter, okay, this is meter. Okay, we have to find potential difference between P and Q. This is very easy question. See, we'll just use the formula. Delta V is equal to minus E dot dr and take point P to Q. Take point P to Q. Then delta V is equal to minus electric field P to Q. Electric field 2xi cap 2xi cap minus yj cap plus z k cap dot. See, we will find dr. We have to take dr. Dr means this is the coordinates of position vector of point P. This is the coordinates of position vector of point Q. Okay. Then in place of dr we can write E dot dr in place of dr dxi cap plus dy j cap plus dz k cap. Okay. Then potential difference is minus P to Q. Dx dot x, dy dot y dot dy, x dot dx, y dot dz, y dot dz. Okay. Then 2xi cap dot dxi cap, 2xi cap dot dxi cap, it will come 2x dx, I cap dot I cap is 1. Then 2xi cap dot dyj cap is 0, dot dz k cap is 0 since I dot j is 0 and I dot k is 0. Okay. Plus, similarly, y j cap minus y j cap, y dot dy we may take, and dy with respect to all is 0, okay, then it is minus y dy, j cap dot j cap is 1, similarly z dz, okay, then minus p to q x square by 2 plus, 2 into x square by 2 plus, minus y square by 2, y dy, integration of y dy is y square by 2 plus z square by 2, okay. Then just use the limit I am doing here somewhere, okay, just one line, minus x square minus 1 by 2 into y square plus 1 by 2 into z square. Just use the coordinates from 2, 0, 1, 2, 0, 1, 0, okay, and use all these coordinates in place of x, y and z. First take value of x is 0 minus 2 square, 0 minus 2 square, okay. Then if you use value of y, y2 is 1, y1 is 0, then this is 1 minus 0 square, then z 0 minus 1 square, okay. Just put these values and you may solve it. It is easier question, okay. Next question. Using the proper limits, we may find change in potential difference if the coordinates are given. Then I think in this lecture we have done some numericals, okay. Go through all these theories and numericals, and at the end of the subject we will approach some better range of numericals, some beautiful numericals to summarize the subject. Okay. Thank you, students. Thank you for your support. Thanks.